Hello, Mr. Stark with a calculus lesson on differential equations. We've got an integral symbol here. We have dx, and if you're watching this video, you know exactly what those two things mean. And if you don't, well, let's see if you could figure it out through the video, or you could go back. So in this video, I'm going to introduce you to differential equations by using initial value problems, which is one of the main ways that we can solve differential equations. But what really is a differential equation? Well, really, it's just an equation that has a derivative in it, or a differential relationship between the x variable and the y variable, if that's the variables that we're choosing. And of course, like many equations, there are solutions to the equation, and in this particular case, the solution is an actual function. So instead of getting really abstract here, let's just get super practical with a few short examples. Let's say we had a differential equation 2x, and we needed to find the solution. Well, we're looking for the function that if we take the derivative, we get 2x, so that function is x squared. But there are lots of other functions that work, like x squared plus 2, and x squared plus 3, and x squared plus pi. So we like to say x squared plus some constant. And what's going to happen if we have a function cosine x? What would be the solution to that differential equation? Well, this is not an equation over here. We could just say y equals, or dy dx equals. Well, the solution to dy dx equals cosine x, well, that's the function sine x. But we could also take the derivative of sine x plus 5 and sine x plus 8, and that constant's on the outside of the function, so what's being evaluated for x? So we have sine x plus c. Well, let's say we had something like, I don't know, secant squared x, and you kind of get the drift here. Where I'm going with this is that I'm just writing down all of the derivatives that come to my mind on the left side here, and we find out what the antiderivative is on the right, which is the solution. So you should remember this one, tangent x plus c. And then one of the most common mistakes that students make, they have this function 1 over x, and we need to find the solution for that differential equation. They say, okay, I'm going to add the power and divide by the power, and I get x to the 0 over 0, some craziness. But that, as you should know, that's natural log of x, and we'll have a plus c on the end. So now we can come up with a bunch of different differential equations, and what's lovely about this is we're just continuing to move backwards in an inverse relationship with integrals as they relate to derivatives. So as we go through this particular unit of study and topics that are in this unit, we're reviewing all of the things that we've learned prior to this topic of differential equations. And just like derivatives, we have a few different ways that we can work with derivatives. Some of the main three ways that we work with anything in mathematics is going to be in the list here. Well, the first way that we'll use to solve differential equations is an algebraic way. And that algebraic way is what we're going to talk about today in this video, initial value problems. The second big way that we'll use to solve differential equations is taking a graphical approach. That tends to be students' and my favorite approach. And that particular method is called slope fields, and its own specific topic or concept. Slope fields are really neat looking, and they could be somewhat complicated, but they don't really give us just a whole lot of information that we can manipulate. So it's sort of limited. And the last way is a numerical approach. And that specific one we're going to use is Euler's method. It's pronounced Euler, not Euler. And if you've ever seen Hidden Figures, you might have heard them mention that in the movie. So in summary, these are the three ways to solve differential equations, and differential equations are actual equations that we're trying to solve, just like these here, and just like we would have done in an Algebra 2 class or a pre-calc class where we're just solving an equation and finding the zeros or something. So let's get to it. I have two examples for you. The first one's pretty quick. The goal is to find all functions that satisfy dy dx equals 3x squared plus cosine x. So the bummer about this example is it's not really an initial value problem because it doesn't give us an initial value problem, an initial value. It says find all functions. So it was kind of like we were doing 2 slides ago. We just want to find any and all functions that satisfy this. So we're just really working backwards. So we're thinking about, okay, what is the antiderivative of 3x squared? So I'm going to say y, the antiderivative of dy dx is y, and 3x squared, so we have 3x to the 2 plus 1 over 2 plus 1, using the reverse power rule. I'm taking you the long way here. And the antiderivative of cosine x is sine x, like we just talked about. And there can be any constant that could be added to that, as long as it's just a constant. So I'm going to call that big C. Later on, things get a little bit tricky with whether we're calling little c or big C or some a value. But for now, we'll just simplify this and we'll say that the answer to this, the solution to that differential equation, is x to the 3rd power, because the 3's cancel, plus sine x plus c. And that is what's called a general solution, not a particular solution. The general solution. The general solution always has some c value in there. We don't exactly know what that is. So if we were given an initial condition, like, oh, when x equals 4, y is 3, then we could plug that in and solve for c. And that's what we're going to do next. So we move from general to specific, or what we could call particular. So here we go. The main word here is particular. Find the particular solution to dy dx is equal to e to the 2x minus 3x. And so here it is. The initial condition says it passes through, the graph of the solution passes through 1 comma 1/2. Now this might get a little bit dicey. I might need 2 pages here. You might need to just organize your work, not write too big. So let's jump right in. The antiderivative, so y equals, the antiderivative of this is e to the 2x. Uh-oh, the chain rule applies. We need to undo that 2 that would be multiplied. So we have 1/2 e to the 2x minus 3x to the 2 over 2. Okay, so that was very basic antiderivative stuff, and we're going to add a c value here. Now that was pretty easy for me, but maybe that's not easy for you. Maybe you need to just double check your work and before you move on and plug in. I say, okay, if I take the derivative of 1/2 e to the 2x, well, it's 1/2 e to the 2x, chain rule, multiply by 2, and the 1/2 and the 2 cancel. Aha, it works. Okay, and I hope you're pretty good with that expression there. All right, so what we're going to do is we're going to take this initial condition, or this initial value, and we're going to plug it in. So 1/2 is our y value. All right, so we're going to plug in that in as y, and then the rest is just kind of jotting down what's there. And then the 1 is the x value. So I'm showing you in red what I'm plugging in. Plug in 1 twice. Everywhere there's an x value, I'm plugging in, and everything else stays the same. So 1/2 equals 1/2 e to the 2 minus 3 over 2 plus c. All right, let's just take one more step and simplify here. So what I notice here is I have this negative 3/2 on the right side of the equation. I'm just going to add that to the left side, well, to both sides really, right? So 3/2 plus 1/2 is 4/2, which is 2. And then I still have my 1/2 e to the 2 on the right side plus a c value. Okay. Now we wish maybe this would be simplified easier, but we're at a point in a calculus class where we shouldn't expect that to all work out nicely. So I'm just going to solve for c here, and c is equal to 2 minus, and I'll just write this as one fraction here, e squared over 2. So that's the c value that I can now use to write in the original equation, which is on the left here. I'm going to rewrite that and plug that c value in. So here's a general solution, that very first thing that we did, and the particular solution, sometimes also called the specific solution. I don't know, it doesn't really matter, but that particular solution is the original function, y equals 1/2 e to the 2 x minus 3x squared over 2, and we're plugging that c value in. Plus 2 minus e squared over 2. And of course you're wondering, oh, there must be something I could do to simplify that. Oh my gosh, that's so ugly. But we can't. I don't know, maybe we could factor a 1/2 and it would just make it look prettier. Okay, that is it. That is a pretty detailed question. You'll come across all sorts of functions that you're going to have to take the antiderivative of. So functions meaning the differential equations that you'll anti-differentiate and work with. So anything from trig to exponential, logarithmic, polynomial, rational, etc. And that was differential equations, the very first topic. Thanks for watching.